Okay, it's time for discussion 3.3, trends in the periodic table. So we're going to look at trends in 4 different properties: atomic radius, ionization energy, electronegativity, and chemical reactivity, which we looked at in lab 3.3. Okay, so first, atomic radius. Down a group. Atomic radius is basically just how large atoms are. Now, there's a more sciencey definition where it's half the distance between 2 nuclei in a bonded molecule, but essentially it's just the size of the atoms. Now, the trend down a group is that atomic radius increases. And the reason this occurs is every time we go down a box in the periodic table, we're adding an additional occupied energy level. So we see here beryllium has 2 energy levels. Not coincidentally, we find beryllium in period 2 of the periodic table. Barium is all the way down in period 6, and it has 1, 2, 3, 4, 5, 6 energy levels. Because we're adding energy levels as we go down, the atoms get bigger. Now, this is kind of like increasing the number of layers in an onion, and a good way to remember it is that each circle gets bigger as we go down. So if we put a snowman next to the periodic table, that will help us remember that they get bigger as we go down. All right, now across the period, the trend in atomic radius across the period is decreasing. Now, the reason this occurs is every time we go one box to the next across the period, we're adding protons to the nucleus. But within a period, all the elements have the same number of occupied energy levels. So that means the nucleus will have a greater attraction to the valence electrons and will pull them all in closer. So with the snowman, we can use a snowman to remember that atomic radius increases going down. Well, imagine the snowman falls over along the periodic table. Now we can see this relationship where they're getting smaller as you go across. All right, ionization energy. Ionization energy is defined as the energy in kilojoules needed to remove an electron from an atom in the gas phase. All right, so the lower an atom's ionization energy, the easier it will become to remove electrons from it. So ionization energy down a group. So the trend down a group is that ionization energy decreases. It gets smaller. That means as we go down a group, it becomes easier and easier and easier to remove electrons from those atoms. Now the reason this occurs is called the shielding effect. So shielding is when core electrons, all those electrons in inner energy levels, block the effect of the nucleus so that the attraction between the nucleus and the electrons decreases. So the more tightly a valence electron is held by the nucleus, the harder it is to remove. So with 2 energy levels, there's only 1 energy level shielding this electron from the nucleus. But with calcium, there's a grand total of 4 energy levels. So this valence electron in the 4th energy level is being shielded from the nucleus by 3 inner energy levels. So as we go down a group, we're increasing the number of energy levels, which increases the shielding effect, which decreases the attraction between the nucleus and the electrons. All right, so as the total number of energy levels increase, shielding will increase. That means that elements in the same period will have the same shielding effect because they have the same number of occupied energy levels. All right, next, ionization energy. Across the period, the trend is that it increases. The reason? Well, the atoms get smaller as we go from left to right. Right? So as the electrons get closer to the nucleus, they are harder to remove. Or the nucleus, they're harder to remove. Right? So we have some a discrepancy here in ionization energy. We just said that ionization energy increases going across the period, and we see that in general, 520 to 2081, it does increase going across the period. But there's a little discrepancy between beryllium and boron. Now, that discrepancy is caused by shielding. So once we go from beryllium to boron, we're going to go from a full 2s to just beginning to put electrons in the 2p. Now that full s sublevel will create a small shielding effect on that electron that's added to the p sublevel. So it makes that p electron a little bit easier to remove. All right, electronegativity. Electronegativity is an atom's ability to attract electrons of other atoms or compounds to itself. It's basically the ability of an atom to steal electrons from other things. Right, now this is a relative ability, so it's a unitless quantity. So if you're ever asked to identify these properties, you can identify them by their units. Atomic radius will be some kind of unit of length, like nanometers or picometers. Ionization energy, since its energy is measured in kilojoules. And electronegativity has no unit, so that's one way to identify the properties. All right, so down a group, electronegativity decreases because of the shielding effect. All right, so again, the nucleus is blocked by electrons in the inner energy levels. Now, nucleus is positive, so the nucleus is trying to attract electrons that live outside of itself. So the more energy levels you have blocking the nucleus, the less effective the nucleus is at attracting electrons to itself. And finally, across the period, the trend is that electronegativity increases, and the reason is because as atomic radii decrease, the atoms get smaller, and the nucleus is actually physically closer to the electrons. So summing up the trends, atomic radius, the trend down as atomic radius increases, and the reason is that we're adding energy levels as we go down the group. The trend across is that atomic radius decreases. That's because we have more protons in the nucleus and the same number of energy levels. Ionization energy down in a group decreases because of shielding, and across the period it increases because they're smaller. Electronegativity decreases down a group because of shielding, and it increases across the period because the atoms are smaller. So you can see here that these trends are opposite from each other. Ionization energy and electronegativity are the same trend, and they occur for the same reasons. Atomic radius is opposite. The reason across is the same essential reason as the other trends, but the reason down is kind of intuitive and obvious. All right, so electronegativity and anions. So an anion is a negatively charged ion, and it's formed by an atom gaining electrons. Remember that electrons are negatively charged, so when something gains an electron, it becomes more negatively charged. It takes on that charge. So which groups have high electronegativities? Well, mainly groups 17, 16, and 15, but in general, nonmetals have high electronegativities. That means in order to become like noble gases, they're going to want to gain electrons so that they can have a full 8. That means that negative ions are made from nonmetals. Now we know that metals and nonmetals are the complete opposite of each other, and since nonmetals are good at gaining electrons, they have high electronegativities, that means that metals are not very good at gaining electrons, but they're great at losing electrons. So ionization energy explains the formation of cations. So a cation is a positive ion, and it's formed by an atom losing electrons. So the groups with low ionization energy are the metals, particularly groups 1 and 2, alkali metals and alkaline earth metals. Now in order to become stable, these elements need to lose electrons. Right? That means that positive ions are made from metals. And that is it for the discussion. If you are interested in learning about the reactivity of metals, look at the lab that we did for topic 3.3. All right, and thanks for watching.